So last time we started section 6.1. We're taking a look at the set of rational numbers. We had talked about different ways that rational numbers are used. We talked about, that was this slide, using rational numbers. We also talked about some different representations and how to make sure that sizes of boxes are the same and stuff like that for representing fractions. We're going to look a little bit more at some history and some modeling today. So some historical facts about rational numbers. Rational numbers were used by Egyptians. So these are very old types of numbers. But the Egyptians always used numerators that were 1. So instead of having a fraction like 7 over 12, that would have been a foreign idea to them. They would have had fractions that looked like addition, 1/4 plus 1/3. So they've measured 1/4 and they've figured out how much more of it they need to add to get to the value they want. So measuring 1/4 plus 1/3. The Greeks adopted fractions with denominators of 60 from the Babylonians. This idea is still presently used in measurements of angles. So we see these ideas of 360 degrees in a circle and things like that present from that. And then the Hindu are the ones who actually developed our modern bar between the numerator and denominator. And that actually came into use in Europe in the 1500s. So fractions are really old. They've been utilized for a very long time. There are 3 basic models for fractions. We saw 2 of these models used last time. We saw the area model last time, and we saw the set model. We haven't seen the number line model drawn. So the area model is the use of a rectangle, and it doesn't even really have to be a rectangle, though that is commonly used. It could also be some other kind of an object, like it could be a triangle or a circle or something else. But rectangles are pretty common. And it's used to break something into pieces, and then you shade a portion of the pieces. We saw 3 examples of this last time in our diagrams. And so if you had something like, we'll do 1/4, you would, let's try again. You would split it into 4 pieces, and you would shade one of them. And this would be the fraction 1/4. Okay, so that's an area model. The number line model, which we have not talked about, you've seen used before. It looks like this. And it starts with the number 0. And for the purposes of fractions, and what we're doing with fractions, we're just going from 0 to 1, because our number 1, we're using the example 1/4 each time. Our number 1/4 is smaller than 1, so I only need to represent 0 and 1. And then the way that I break apart the number line is I break it in halves, and then I would break it into halves again. You're fine. So this is in 4 pieces now. So I have 1/4, 2/4, 3/4, and then 4/4, which is 1, is where I would end. So 1/4 specifically would be right here. And I would designate that that's my value by putting a point on that line. I'll put mine in a different color so that it's very clear. This is the number 1/4 in a number line model or a measurement model. And then the set model actually uses objects where each of them are whole number or whole size pieces, and we partition it. So we saw this last time. So I'll do circles, but they don't have to be circles. So this is they're calling them chips here. And so if I want 1 chip out of 4, I'd have 4 chips. And then one of them would be like shaded in or whatever. So this would be representing 1 object out of 4 objects. So we're sort of partitioning whole objects into pieces. This works just fine if I have control that the denominator 4 is the same as the number of chips. Right, that's fine. But if I have 5 chips and I want to shade 1/4 of them, that's not simple to do, right? It's like having 5 cookies and dividing them among 4 kids. It doesn't work real well. Right? Mom should just eat a cookie. That's what should happen. And then you've got the 4 cookies and we're just fine. But when I can control the denominator, this works fine. So this is a set model. So we're going to do some theorems, some application pieces of how we use fractions with equations and whatnot. And the first one we actually have is the fundamental law of fractions. The fundamental law of fractions says that if we have a fraction a over b, and we have any other non-zero integer, Okay, so you've got 7, you've got -2. Doesn't matter if it is positive or negative, just not 0. If I multiply the numerator and the denominator by that same value, the fraction's value as a whole doesn't change. Okay, and we know this to be true. We've done this repeatedly. We do this not only from left to right on the screen, you've done it from right to left where you've reduced things as well, right? You've looked at things and said, look, it both divide by 2. Since they both divide by 2, I can simplify my fraction, right? This is a caveat of what this theorem is telling us. So this fundamental law of fractions tells us that we have equal fractions if we've simply multiplied the top and the bottom by the same value. Simplest form is the sort of backwards version of that. We actually would say that A over B is in simplest form. When we have the denominator positive, B is positive, and the greatest common divisor of A and B is 1. So another way of saying that is that A and B don't have anything in common that they divide by. There's no common factor I can divide them both by. And this is what we would sometimes refer to as being reduced, right? Or simplified fractions. We call them both of those things. And we typically like our answers in this form. We like to see them in this simplified form when we get to that point. So we're going to take a fraction. It's 7 over -14. And I want you to take a couple minutes, however long it takes. It's not going to take you very long. And I want you to write 3 other fractions that are equal to 7 over -14. Once you've written your 3 other fractions, touch base with somebody nearby you, in front of you, behind you, to the side of you, or whatever, and confirm that you both have the same kinds of work going on. They don't need to be all the same. There's infinitely many answers here, okay? But write 3 other fractions equal to this one. I'll start you out with one, okay? I'll start you out with one. Here's 7 over -14. One option is I could multiply the top and bottom by 2. And if I did that, I'd get 14 over -28. So that's another one. Okay, so find other options that are equal to 7 over -14. Somebody tell me a number you got. Chesney.
So 21 over -42?
21 over -42. Yes, ma'am. Something else. What do you have?
1 over -2.
Yeah, 1 over -2. So how did you get 1 over -2?
7 is half.
Yeah. So you could look at the fact that they actually have a number they both have in common and simplify or reduce them, right? That's the other version we did before. Good. Okay, what else do you have? You want to see a really creative one? How about that?
Interesting.
Yeah, right? In essence, what I've really done is just shifted the negative, but the reason it makes sense is because I've multiplied the top and bottom by -1, which is what does that. So all of these versions can have the negative move to the top or the bottom. All right, somebody give me one more. Ooh, you got a big one, huh? Okay, I'll add one more to it. What about 3 over negative 6? Now, if I start with the negative 7 over, or the 7 over negative 14 and try to say that that's equal, that's harder to see. But if 7 over negative 14 is equal to 1 over negative 2, and 1 over negative 2 is certainly going to be equal to 3 over negative 6, right? So the original one and this one would also be equal. Kind of go through steps to see it. So there's infinitely many different ways that we can create equivalent fractions. Now, there is only one simplified form for every fraction, though. Now, this one is written in a little bit different way, and it's on purpose. So if I'm looking at 42 squared over 35 squared, what would I do to figure out the simplest form? Well, one option is to take a look at what 35 and 42 actually break down into. So what is 42 if I factor it? 6 times 7, okay? And since 42 is squared, 6 times 7 is squared. What is 35 if I factor it? 7 times 5. Okay? Now, what does squaring mean? We're going to talk more about powers in section 3, but what does it mean if you square something? It means it times itself, right? So you'd have 6 times 7 times 6 times 7. And you'd have 7 times 5 times 7 times 5. Now, simplest form, back on the previous couple slides ago, actually 2 slides ago, said that I'm able to reduce anything on the top and on the bottom, right? Divide it by the same quantity. Do you see a number that we can reduce this fraction by? 7. And not only do you see it happen once, you see it happen twice, right? So this leaves me with 6 times 6 on top and 5 times 5 on bottom. Now, will that reduce any? No, because 5's prime. 5 doesn't divide by anything but itself and 1. And 6 doesn't divide by 5, right? Not evenly, not in whole numbers. So our final answer would simply be the multiplication of those two pieces with one another. So 36 over 25. Now, it's really tempting to go back up here to the original problem and do what? What would a student incorrectly do that's really tempting to do? Yeah. So it's really tempting to either multiply out 42 times 42. Did anybody think to do that? I think that's what Taryn said. That's really tempting for some people. And then the number gets a lot bigger. But that's not helpful when we're trying to reduce it, right? We don't want it to get bigger and then to reduce it. So we want to try and keep it reduced. There's something else that's really tempting to do here too for some people. To cancel out the squares. Do you guys see the squares? So it's sort of like take a square root of the top and the bottom kind of feature. We don't have that ability. And the reason we don't is because the squaring is multiplying it by itself, right? It's not multiplying it by something that's the same on the top and the bottom. So there's no cancellation of squares. There's no taking of square root tops and bottoms. And we don't really want to multiply it back out because that's unhelpful. Okay? So this is a nice way of doing it, of reducing it this way. It's not the only version, but it's the version you guys saw, the most simple, and I think that's a really good one. Equivalent fractions. How do we know if fractions are equivalent? Like, well, we created some equivalent fractions before. We created them by simply multiplying or dividing top and bottom by the same value. But we can actually compare fractions and to decide if they're equal when given two values by doing something called cross multiplication, right? We can decide if this one, A over B, equals the C over D, right? If that's the question, by simply multiplying A and D together. That's not what I meant to do. Try that again. Multiplying the A and the D together, multiplying the b and the c together. And if we get the same product from the multiplications of the diagonals, then the original fractions were the same. So let me just give you a really quick example, because it was a sort of an odd thing maybe for me to say that 7 over negative 14 was equal to 3 over negative 6. Now, if you want to deal with the fact that they're negatives and keep the negatives in, you can, but we can also kind of just ignore them because they're the same. So checking this is the same as checking if these two are the same. Agreed? They're both negative. So somebody grab some, well, you know this one because we just did it. What's 7 times 6? That's 42. And then whether you've done it in your head or whether you want to do it right here, what is 14 times 3? It's 42. They're the same. So it checks out. The multiplication along diagonals are equivalent, which means the original fractions were equivalent as well. Okay, that's what this theorem is telling us. Now, here is an example. We have 3 over negative 12, and we have negative 36 over 144, and it's asking us to decide if they're equivalent. There's at least 4 ways to do this problem. I'm not asking you to do 4 ways on your homework, but I do want you to recognize the different options that you have. Number one, because sometimes it's more obvious to do it one way than another, right? So having those options is good. Number two, you're going to see this happen multiple times in this course and in number theory if you ever take number theory, and in geometry if you take geometry, is that we want to show you lots of options because you've got kids, and do you know what? They don't all learn the same. And so what's going to make sense to Taryn may not make sense to Chesney, right? Or to Jamora. So I'm going to pick on the people I already know. It may not make sense to do it that way in your mind. And honestly, part of this isn't even about your mind. It's about the minds of the kids you're teaching. And so having a toolbox with different options available is going to allow you to be a better teacher in the future. So the first way that we're going to do the problem is using this theorem that we just talked about. It's a good place to start. We just gave a theorem on how to do this. Let's utilize it, see how it works. Again, both of the fractions are negative. So I'm going to ignore the negatives because we know the negatives match. That's not the part of concern, right? So we're just going to focus on 3 over 12 and 36 over 144. So the first way we're going to do this is with theorem 6.2, where we're going to take the 3 over 12 and the 36 over 144, and it's really like a question mark equal in between, and we're going to verify it by multiplying along diagonals. And you're welcome to grab a calculator out to multiply these. These are kind of big numbers. If you were working with small children, they'd be using smaller numbers for the same thing, and they'd be able to do the multiplication quicker, and that's fine. What is 3 times 144? 432. And what is 12 times 36? 432. These are equal, right? So theorem 6.2 tells us that yes, we have equal fractions. Okay, so that's lovely. Now, what happens if you're in a place where you're doing something with fractions, but the kids aren't allowed to use calculators, and somewhere along the way they never memorize their multiplication tables? This might not be your best bet. You might just have created a source of frustration for them, and they don't like that very much. That's a possibility. So we're going to give some other options. Let's take a look at option number 2. Option number 2 is we're going to simplify and compare. Okay, I'm going to start with 3 over 12. 3 over 12. Okay, well, 3 and 12 are not values that are prime. They both divide by things. In fact, they both divide by something in common. What do they both divide by? Yeah, they both divide by 3. So if I divide 3 by 3, what do I get? 1, and 12 divided by 3 is 4. Okay, fantastic. That's the simple one because it was the smaller of it, right? The other one is 36 over 144. And we are certainly, it's an option anyway, to divide this in steps, right? Like I can say, okay, well, I recognize that they're both even. I'll divide them by 2. Or you might look at this and say, okay, well, yes, they're both even, but I actually am pretty sure they both divide by 4, which is a little bit bigger than 2, so I'm going to start there. We're going to do 4. So let's try 4. So if I divide 36 by 4, That's 9. What's 144 divided by 4? It's 36. Okay? And then you look at this. That's what you said, right? I heard you right, yeah. You look at this and you're like, okay, well, 9 and 36 both divide by something. And you might recognize they divide by 9. You might not. You might only recognize that they divide by 3. But they do divide by 9. And it gives you the 1 over 4. And so in reducing these are equal. So that means the original fractions were equal as well. That's kind of the approach in a backwards kind of way that I got 3 over 6 just a minute ago. Right? 3 over 6 reduces to 1 over half, 1 over 2, just like 7 over 14 reduces to 1 over 2. They both reduce to the same thing, so they have to be the same value. Okay, so these are equal fractions. Let's do common denominator next. Common denominator simply means the denominators need to be the same. Our fourth one that we're going to do here is going to be the least common denominator. So yes, it's a common denominator, but it's the smallest one available. So we're going to do common denominator first. So if you're trying to do this with a common denominator, what you're trying to do is get the denominators to match. And the simplest way to get denominators to match, right, the most straightforward way, is to multiply the denominators by one another. In other words, we're going to multiply 12 by 144, top and bottom. And we're going to multiply the 144 by 12 on the top and the bottom. Okay, and keep in mind, these are all, again, bigger numbers your students are going to be working with. I get that. It's just an example. So with your calculator, what is 3 times 144? What is it? That was the 432? Okay. What is 12 times 144? All right. So the denominator is the same because we multiply the exact same values together, so it's 1728. What's 36 times 12? $432 again, right? So again, we were able to get common denominators and the numerators match, so these are equal fractions. All right, least common denominator means that we actually want to find the smallest denominator that they have in common. And this is actually a pretty nice way to do this particular problem. And the reason is because most of the time, if kids have memorized multiplication tables, they've memorized up to 12 times 12. I don't know why we do 12s these days, by the way. We didn't do 12s when I was in school. We stopped at 10s, and it still makes more sense in my mind to stop there. But 12s seem to be the popular place for people to stop these days. And so they very likely know that 12 times 12 is 144. That is not an uncommon thing for somebody to know. So we can multiply this one by 12 to get the denominators to be in common. Now they're both 144. And then 3 times 12 would be my 36. Again, these two things now are equal. I didn't mark them, but these were equal as well. So the original fractions are equal. Now, in your homework, it's going to ask you, maybe in your group work too, to decide if something's equivalent fractions. Just pick a way to do it and do it. I'm not asking you to do it 4 ways. I just want you to be aware that there is more than one way to do this problem. Now, not only in 6.2 are we able to cross multiply and to check if something's equivalent, right? Do we have equal fractions? We can use that same idea to also decide if fractions are bigger or smaller than one another. So if we have fractions a over b and c over d, then a over b is bigger than c over d. If when we do this same cross multiplication feature, the AD, so you have to start in the top corner for this to work, a times d is bigger than the other diagonal c times d. We have to be able to do it in the right order, otherwise we're going to get it backwards to do this. But this works. So if you were trying to show, for example, right, like that 1/2 is bigger than 1/3. It is. 1/2 is bigger than 1/3. We can actually do this by multiplying this diagonal together first. 1 times 3 is 3. And then the orange diagonal here together second. 2 times 1 is 2. And in fact, we see for sure that 3 is bigger than 2, so 1/2 is bigger than 1/3. Okay, so it's a pretty quick way of checking to see the size and compare them to one another. It doesn't work real well if you have a list of numbers, though, right? So our next example, we don't just have two numbers we're comparing, there's three. Well, I can only do this process with two numbers. There's no way to add on a third and make that make sense. I'd have to do two numbers at a time. It would actually be a very convoluted and confusing way of doing it, to do it two at a time for three numbers. So when I'm looking at this next problem where I want to put three numbers in order, it's probably not going to be your best bet to do Theorem 6.3. But you can use one of those other methods that we just did on the previous example, where you're finding a common denominator, or you're finding a least common denominator, or you're reducing potentially, maybe if that would work. So on this one, we're going to find a least common denominator. It is a very nice way to do this particular one. So if you take a look at 25 and 10, what is a common denominator that we can get for 20, for 5, and for 10? 20. 20 is a really nice number for this. The first one's already in something over 20. It's 13 over 20. The 5 would need to be multiplied by what? 4. So that would actually end up giving me 12 over 20. Get the numbers right. And then what would I need to multiply the 10 by? 2. And that would give me 14 over 20. So if I compare these numbers now, which one's the smallest? 12. This one's my smallest. What's my second one? The 13 over 20. This is my second. And what's my largest? The one at the bottom, right? But then in writing out my answer, I want to write them from smallest to largest, like it said, but with the original notations that I was given. So the smallest number, 12 over 20, is actually the number 3 over 5. And it is smaller than, so I'll use a less than sign. The next one, which was 13 over 20, that's how it was given to me. And the largest, which is 14 over 20, but it is 7 over 10. So common denominators would also work for this. It would be fine if you wanted to do a common denominator. You're just going to get bigger numbers. Least common denominators works really nice. Okay. Now, this one actually asks us to compare greater than, less than, or equal to. And we do have just two numbers. So one option would be to use Theorem 6.3, where we do the cross multiplications and check them that way. It's not the only way to do the problem, but it doesn't work too badly. We could also get common denominators. It actually works really nicely to get least common denominators on this problem. What do you notice about these two denominators? Can you see something nice? Yeah, one of them is a multiple to get the other one, right? So one of them is 215, right? 215 times 2 is 430. So this particular one works really nicely to get a least common denominator as well. There's also a third way to do this one. We'll show all three of these, but intuitively, you should be able to look at this and tell me which one's bigger. They're very different sized numbers. They're not close, like 1/2 and 1/3, and you're like, I'm not sure, that bigger number in the denominator, how does that work? They're significantly different. Which one's smaller? The first one or the second one? Can you tell? Which one is it? Maybe you can't. Okay, well, we'll do that one third then, and we'll talk about how we think about that one. Let's try this with Theorem 6.3 first. So if I do Theorem 6.3, I actually contend that this is the hardest way to do this particular problem because the numbers are kind of big. And so the multiplication ends up being kind of ugly. So in order for me to check which symbol needs to go in between, I need to do 21 times 215. And yes, your calculator will do that just fine for you. And then I need to do 51 times 430. So what is 21 times 215? Yes. And what is 51 times 430? Okay, so clearly the 21,000 is much bigger, right? Much bigger than 4,500. So back up here, the symbol that should be there is the less than symbol. Now we know the answer is that the first fraction is smaller than the second one. I asked you to do it intuitively, and there were some fuzzy expressions. You know which one's going to be the answer now when we come back to that point. Let's do it the second way that we had talked about, which is with the least common denominators. So 21 over 430. And I have 51 over 215. And we talked about the fact that if we multiplied the second one, the 215 by 2, we would get 430. And what do we get on top? What's 51 times 2? 102. Very clearly 102 is bigger than 21, right? So the second fraction is bigger than the first, like this. Okay, so let me mention this one that allows us to get some sort of an idea of the size of these things. And I'm going to call it estimating. So if you look at we'll do 51 over 215 first. 51 over 215 is almost, I don't know why I moved that over there, is almost 50 over 200. Like it's close, right? What is 50 over 200? It's 1/4. Think about having $2. How many 50 cents are there in $2? Well, there's 4. Right? There's 2 sets of 50 cents and $1, and you have them in 4. This is 1/4. Okay, so it's about 1/4. But what about the other one, which is 21 over 430? Again, it's approximately 20 over 400. Now, you can probably automatically just recognize, we could have done this with the 52, that we can knock off a 0. The 2 and the 40 would then each reduce by 2, so this would end up giving us 1 over 20. 1 over 20 is the equivalent of a nickel. And 1 over 4 is the equivalent of a quarter, right? Quarter or a nickel. Please, I'll take the quarter. That's fine. That reminds me of my daughter. She likes to get all the quarters at Aldi. Do you guys do that? That's what my little one does. She loves going to Aldi. She ended up with 7 quarters one time going to Aldi. It's crazy. All right, that aside. Denseness. Denseness means that between any two rational numbers, there's another rational number. So if we have A over B and C over D, those are rational numbers. There will be space between them, and there will be another rational number in between. And you probably have thought about this from a graphical perspective before, right? If you look at a graph and then you zoom in, and it looks like becomes more space in between. There didn't get more space, right? It just got bigger looking. And in that space between it, there's more numbers. And there's more numbers, and there's more numbers, right? So there's always a number in between two other rational numbers. Now, that doesn't work for whole numbers, right? There is no whole number in between 3 and 4. There's not. There's no other whole number. There's other rational numbers in between. But this is a property about rational numbers that does not exist for whole numbers or for integers. Okay? Any two numbers, there's another rational number. This is actually a very easy way of finding that number or a number of that variety. It's not the only number between them, but it's one of them. So if you have A over B and C over D, if you add the numerators together and you add the denominators together, you will get another number that's in between A over B and C over D. Now, that's way easier than the idea of saying, okay, well, we can do this with whole numbers really nicely. Let's take our whole numbers 3 and 4. If I want to find the number halfway in between 3 and 4, I can do that by saying 3 plus 4 and divide by 2. That's not bad, right? 3 plus 4 divided by 2. Okay, great. It's 3.5, 3.5, no big deal. 3.5, 7 over 4 over 2. Like, there's lots of ways to write that. Great. But what if you have something like 33 over 427 and 7 over 92? I don't know about you. Actually, I do know about you. I absolutely know that you do not want to add those two numbers together and divide by 2. And I don't either. That sounds terrible. These are really ugly fractions. I don't see a good way of getting a common denominator to add them together even. Like, they're bad, right? But having this theorem allows me to do this in a very simple way. It says I should be able to add the numerators together, 33 plus 7, and add the denominators together, 427 plus 92. And I will get a number that is in between the two original numbers I was given. So 33 plus 7 would be 40. What is 427 plus 92? 519. And if it reduced, we would reduce it here. This one does not reduce. 40 divides by 4s and 5s, and 519 won't divide by 4, and it won't divide by 5. Or 2s and 5s, either way. So 40 over 19 is actually a value that's in between it. Is it the only one? No, there's infinitely many, but this is one of them, okay? So why must there be a number between these fractions? And the reason is because rational numbers are dense. And we're using the word dense here like the word thick, right? And I don't mean thick like stupid, right? Some people use the word dense like that. That is not the context here. Dense means it's really dense like a cake, right? Really thick, okay? It means there's a lot of substance there. There's a lot of numbers that are in between there. Numbers are dense. So the reality is that this between any two rational numbers, there is another rational number. So the reason this has to exist is because the two numbers are rational. And we know that between any two rational numbers, there's another rational number. Okay, we're going to take a look at a student error kind of problem. We have a fraction given to us as m plus n over p plus n. And a student reduces the fraction to m over p. So the first thing I'd like for you to consider, because if you get a student's work and they've done something like this, you probably first should figure out, what did they do? Because if you can figure out what they did, you can usually help them to understand why it didn't work. If something did something wrong. So what did they do?
Just cancel out the ends.
Yeah, they canceled out the ends. That's exactly what they did. They canceled out, and I'm going to write it a little bit differently. They canceled out the plus n, right? Because there's an addition of n on the top and the bottom. They canceled out the plus n's, okay? Why might they think that this is okay to do? Because it is okay to cancel things out sometimes, but they can't do it like this. So why might they think, well, I'll just cancel this out?
Because it's the same on top and on bottom.
Same on top and bottom. And when are we actually able to do something like that?
Whenever it's the same exact number.
Same exact number. What did you say? When it's multiplication. So when the same exact number is being multiplied, we can do this. This isn't being multiplied, right? There's something different going on. It's addition. But that's why they might think that this is okay to do. Yeah? Okay. So why might they think this is okay to do? And it's because we do this for multiplication. And we can even write down that if we had this same thing, we have m times n over p times n, we would be able to do this, right? And we would end up with m over p. All right? And that is valid. That is a valid operation for multiplication. So besides just telling them that works for multiplication and it doesn't work for addition, which is a very true statement and not very helpful. Right? It's not very helpful. How could you show them that this really doesn't work?
Just by adding
Okay, but we've got letters.
it. Putting actual numbers into the equation.
Yeah. That's a really good way to do it. It's a very concrete way to do it. So yes, we want to add them, but if we add them with some numbers in, we can see it's not going to work. Sometimes you need to be a little careful about putting numbers in things because sometimes you might accidentally choose something that does work. That would be very unfortunate, right? So be careful. But most of the numbers won't work for this one. So somebody give me some original numbers.
5 and 11.
5 over 11, and let's add something to the 5 and the 11. What do you want to add?
7.
7, okay. So what's 5 plus 7? 12. How about 11 plus 7? 18. Now, 12 and 18 do reduce, so we managed to get something that's going to be able to be reduced, so we need to check that. So what will they both divide by? 3. What's 12 divided by 3? 4. And what's 18 divided by 3? 6. Oh, it gets to bitter. We need to divide again. What can we divide by now? 2. All right, so if I divide these by 2, I get 2 over 3. So 2 over 3 over here, and if we just canceled like we did, like they wanted to do, we'd have 5 over 11. So what in the world can we say for why 5 over 11 and 2 over 3 are not equal? There's several things we could say. How do I know those aren't equal?
You could do cross multiplication.
You could cross multiply and show it, right? Theorem 6-2. You could definitely do that. You could also justify that they're both in simplest form. And they're not the same. If they're in simplest form and they are not the same, then that doesn't work. Let me tell you one thing you can't do, and some of you might be tempted to do at some point along the way in chapter 6. You can't turn anything into decimals and justify it from a decimal perspective. And the reason you can't is because in the process of the way this is being done, we're going to talk about decimals in chapter 7. We haven't talked about decimals yet. We'll get there. There's nothing wrong with justifying things with decimals, but that's a different component of what we're doing. We're going to focus on fractions only here, okay? So yeah, these are not going to work. Something else that you might want to do is, this would be a lot, I don't think this is a good way to do it, by the way, but I'm just going to mention it for the students that you have who are going to be like, but Miss Long, right? Miss Long, what if I try this? You're going to be like, I don't know. What are they talking about? This would work. You could actually take the two fractions that they're saying are equal and do the cross multiplication there. You could actually cross multiply there with all the letters involved and see that the letters on the left are not going to equal the letters on the right. It's not very intuitive. I don't think it's nearly as helpful as putting numbers in, but it is a way that would work, right? It is a way that would work. Okay. So we're going to take some numbers that are equal to 1/3, and we're going to make them points on an XY axis so that the numerator becomes the X coordinate and the denominator becomes the Y coordinate. So let me just take the number 1/3 to show you what this is telling us to do. They're saying we're going to take 1/3 and we're going to make it the ordered pair 1, 3. That's all they're describing. And we want to do this for other things that are equal to 1/3. So what is another fraction that's equal to 1/3? Don't overthink this. 2 over 6, you bet. And so that would give us the ordered pair 2, 6. Let's do something that's negative. What would I have to do if I introduce negative numbers? They'd have to both be negative. Very good. So I could do like -1 over -3, right? I could. Let's do one more. How about we do 3 over 9? Are you good with that one? All right, 3 over 9 would be 1 over 3. And we're going to graph these. So sketch yourself a little graph. I think I have some graph paper over here. I do. And we're going to plot 1, 3. That'll be right here on my graph. We're going to plot 2, 6, and 3, 9. And -1, -3. Those are the 3 pairs, 3 points that I have. Okay, what kind of graph is this going to give you? What's it look like? No ideas? It should look like a line. Does it look like a line? I mean, we haven't connected anything yet, but if we attempt to connect them, it should look like it's a line. And it is. There's a little caveat to that. It's not exactly a line. Now, almost all the points on this line, almost all of the points along this line, if we take them, even if they're not at one of these like corner values, like we use this one, say right here, right? It's some kind of a fraction or decimal, in the x direction and in the y direction. But if we divide them, they're still going to give us 1/3, okay? There is one point that will not do that. Do you know where it is? It's right in the middle. What's that point? 0, 0. What happens if you take 0, 0 and try to turn it into a number like we've been doing? That's an undefined operation. I can't divide by 0. We talk about it in number theory, why we can't divide by 0, but it doesn't have a defined form. 0 over 0 does not equal 1/3. At the very least, you know that part, okay? It's definitely not going to be equal to 1/3, but every other point along this line is. So over here, when it describes, it says, what kind of graph do we get? We get a line. The line has a specific slope. Can you tell what the slope is from the line? Right, rise over run. How much do you go up? How much do you go over? What's the slope? It's 3 over 1. We go up 3 and over 1. So it's a slope of 3. Okay, this is a line with a slope of 3, but a hole at 0, 0. 0, 0 doesn't work. Otherwise, it's a line. It's a very well-behaved, very nice line, but it doesn't go through 0, 0.